coordinators. So if they ask me to provide this, so I'm ready to provide. So let us see that. I'm going to show today like simple stresses and strains. First of all, simple stress and strains we are going to discuss. Then come to the complex stresses means it is not simple. That means simple stress means like everybody knows that stress equals to load by area, P by A. But whereas when you move to the complex stresses, it will not be like a 1D, one dimensional P by A. It may move to the 2D or 3D like that. Okay, like principal stresses, principal strains, like plane stress problems, plane stress problems, like that. This all will come into picture in the complex stresses. Then come to the SFD and BMD. SFD means shear force diagram and bending moment diagram. So SFD and BMD are most important things and chapter also. Why? Because based on that SFD and BMD magnitudes only, you will decide uh, the percentage of the steels which you are supposed to provide in the different structural components. So this is I'm talking about civil engineering point of view. Even for the SFD, BMD are very important for the mechanical also. Like based on that, they will design the like shaft thickness, shaft length, even if you talk about the like hydropower plants, their role also there. Always three engineering branches only according to me. One is mechanical and civil and electrical. These three engineers always will be there in all kind of like irrigation projects and so many jobs. These three engineers are interconnected. Of course, engineering started with these three core branches only. Later on, there are so many sub branches has come. So that's where different type of engineering uh, programs we are seeing now. Like computer science also earlier it was not there. Like electrical from electrical only everything has come out. Then EC, like IT, is all and all expanded. Okay. Then come to the pure bending. So pure means what? So pure means so for that there is a one expression F by Y equals to E by R. So based on that equation only, this whole pure bending theory concept will vary. Then come to the shear stresses. Then shear stresses means like different shapes are there, like rectangle, T shape, I shape, uh, triangle, um, like L shape. These all for all the shapes. How the shear stress distribution will vary, and what is meant by shear stress. First of all, that concept also we are going to see. Then torsion. Torsion means it is also nothing but a one kind of movement only, but it is along with the uh, longitudinal axis of the beam. So it is like a twisting movement. So that is nothing but a torsion. But a torsion topic is very important for the mechanical people because they have shafts, machine designs. So in that everywhere torsion will come into picture, like vibrations, like twisting movements only they used to face rather than regular movement. And slopes and deflections. Slopes and deflections are again important for both branches like mechanical and civil. Slopes means what, and deflection means what. In that concept we are going to see. Of course, uh, dx by dy means x with respect to differentiating with respect to y means that is nothing but a theta. Theta is nothing but a slope. Then again, one more time you are differentiating the slope means you will get the deflection. So again, you are differentiating one more time. Deflection means that means d square y by dx square means it's nothing but a movement. Sorry, slope, movement, and again one more time you are differentiating means it will go to the shear force. Then one more time differentiating means it will go to the load, unit load. So from unit load is having power of 4 actually. That means due to power of 4 x by dy 4. Okay. So like that, when you are derivating the from slope to like slope to bending moment and shear force, like that is coming. But first of all, x means deflection. X deflection you are differentiating with respect to y. One time means that is slow. Then again another time differentiation, bending moment. Another time differentiation, shear force. And again differentiation, load actually. Then again from there, if you do the integration, it will come back to deflection. So that everything you are going to see here, like there are different methods to find out the slope and deflections, like Macaulay's method, double integration method, moment area method, even conjugate beam method like that. Then come to the columns and struts. So columns and struts is also very important, and there are few compulsory questions always in the gate. They will try to ask like what is Euler's buckling theorem, and what are the boundary conditions, like when you have the two edges are fixed, two boundaries are two connections are fixed, and one connection is fixed and another connection is free, and one is hinged and another is fixed, like that as per availability of the boundary conditions. You have to find out the Euler's buckling theory formula for the buckling load of the column. Then struts, columns and struts are like both together will come. Then propped and fixed beams. So propped means it is not a cantilever; it is a statically indeterminate structure, whereas cantilever is statically determinate structure. Propped cantilever means for cantilever you are providing one prop at the free end. So that means it is becoming into the statically independent structure. Then come to the fixed beams. So in all our buildings, wherever you see the beams, like rigid connections, these all are like fixed beams. But fixed beams are, it should rest on the compulsorily on two columns. Compulsorily on two columns. Then next one is strain energy. So strain energy is also a very good approach to find out the so many internal effects of the structural members, like deflection, like strain, slope. Okay, these all components you can easily find out by using the energy strain energy methods. So that is also there. So that is of course it's the last topic. Let us see how the things are there, like in the simple stresses. Like we would like to know how stresses will develop and how the things will happen from basics onwards. We'll try to see. Later on, we'll try to move on to the some written notes. Of course, I prepared notes that I'll show, and some other notes prepared long back, that is also I included, and even previous gate papers on simple stresses with solutions. That is also I have included. With these 2 hours, we'll try to discuss these all things, and we'll try to give the summary on this. Yeah, first of all, when we start the introduction to strength of materials, so that is the introduction to SAM, that is nothing but strength of materials, and aim of the subjects, assumptions, and loads. If you see the gate weightage, strength of material, it has 10 plus 2 for mechanical, as I told you already, and 5 plus 7, it is already told by in the last time. Even during the today also, the starting time I have mentioned that for civil this much weightage is there. Then come to the simple stress and strains point of view. First of all, if you take the one body, like which is in rest mode, because we must talk about now only statics. Okay, we are not discussing about dynamics, because strength of material, as you know that when you are observing the like behavior on the deformable bodies, you can see here strength of material is nothing but a study of deformable bodies. Whereas engineering mechanics in the first year you might have studied, that is study of rigid bodies. Rigid body means it won't move, but it will try to displace actually. It never deform or deflect. It will try to displace, because rigid body is there, you can move on that, you can move that. But whereas in the strength of material, it is a deform. That means there may be a blade, it's a beam, like that. So these all things can be maybe happens. Okay, with this, first of all, if you take the one body on any structure, if you are applying on that some external forces, so nothing but a loads. So that due to that load, that body is trying to deform actually first. So when it is deforming, when it is deforming, automatically strain will come into picture first. Why strain will come into picture means the definition of the strain is lateral strain by longitudinal. Sorry, change in length by vertical length. So change in length by vertical length, how it is coming? Because of deformation only. Earlier it was like a 1 meter. Now after applying that one, it is changed into either shrink. It may happen shrinking. It may have a large expansion. So if expansion happens, the L plus delta you have to consider. If it is shrinking, you have to consider L minus delta. However, L minus delta by L or L plus delta by L. So both we can take it in same way, but strain will come into picture first after applying the loads on the body. That body is try to deform. Along with the deform, the strain will come into picture. So stress is depending on strain actually, but strain is not depending on anything. It's an independent thing actually. Uh, so automatically stress will come into picture after strain. How it will come into picture? Like as you know, for different materials, like if you take the concrete or steel or any materials, if you take wood or something, for everything you have a Young's modulus. Young's modulus, how it is coming? It is coming from the practical observation. Like you have a universal testing machine, or for mechanical people there is a one machine called Instron. It's a very sensitive machine. It's around more than crore rupees. It can be useful for the like to testing the small when glasses fibers. They used to check the fibers also, how much tensile strength is there. So like that, when they are testing the either tensile strength or even compression tester, so there the slope of the stress strain diagram is nothing but a Young's modulus actually. Correct. So up to the proportional limit is there in the elastic limit. So the proportionality, it obeys the Hooke's law. So in that proportionality, you have a slope of the Young's modulus. So that's why for the steel, it has been decided 2 into 10 to the power of 5 Young's modulus. Correct. So based on this Young's modulus, you can easily find out the stress here. So Young's modulus equals to stress by strain. So once you know the strain and once you know the Young's modulus, stress automatically come into calculation or come into picture. So that's all about the this is the sequence order, of course. This is the sequence order of loads to deformation and strain and stress. Then E is nothing but Young's modulus. Young's means it's a name. Young's is a person. Modulus means he found the one modulus value for different materials, and stress is we are indicating here sigma, that has the units of Newton per mm square, and nothing but a megapascal actually. 1 Pascal equals to 1 Newton per meter square actually. When you're converting into Newton per mm square, uh, 1 megapascal equals to 1 Newton per mm square actually. Okay. Then strain is nothing but a epsilon. So that we will try to measure in the percentages. Then ES equals to modulus of elasticity or Young's modulus, that is 2 into 10 to the power of 5 Newton per mm square for steel. For aluminum is different, for wood is different, even for concrete, if you ask me, I can tell you that is from the code book, it is there from IS 456 code book, that is EC equals to 5000 root FCK. FCK is nothing but a compression strength of concrete. Okay. Then 1 Newton per meter square equals to 1 Pascal, and 1 megapascal equals to 1 into 10 to the power of 3. 1 into 10 to the power of 3 Pascals. So Pascal is nothing but a 10 to the power of 3 Newton per meter square. Then 10 to the power of meter square, Newton per meter square, you can convert like this. 10 cube and 1000 square. This becomes cancels. Then you are changed from meter square to mm square. No? Then this mm square will remain same there. So that means 1 megapascal equals to 1 Newton per mm square. Like this way, you have to convert the units actually. Then, as I told you, engineering mechanics is a vast subject. So we are studying on the rigid bodies. So that part, of course, we have seen, but the coverage of the syllabus on the engineering mechanics is very meager in the GATE examination, whereas strength of material is our main focus today in this class. So strength of materials is a sorry, strength of material is a study of on the deformable bodies. Okay, okay. Let us see. It is a rigid body, and when you are applying the some load here, when you are applying some load here, as in the form of P, like you are pushing. So this will try to displace. You see, from here to here it is displaced actually. Correct. From here to here it is displaced. That means this delta is nothing but a displacement. And in the rigid body, what is another advantage? Whatever the A is a one molecule, if you assume A and B, these molecules are not changing their position. It's remains same place. Correct? Because the body only displays from one place to another place. So that is only happens in the rigid body. It is nothing but a relative position of the molecules remain same. That is the meaning of your rigid body behavior. Then come to the deformable bodies. When you are applying the some load in the form of tensile forces like this, so this will try to deform. Okay, it is deforming inside the arrow, the dotted lines you can see. But what happens? Earlier A and B were here, but due to this one, due to the deformable nature of the body, A and B are shifted to somewhere. You see, so this is nothing but a not a displacement; it's a deformation. Okay, so here you can see L is original, and whereas delta is the deformation offset, that is L plus delta, total L plus delta is nothing but a your change in length actually. So that is delta is nothing but a deformation. You can see that you can read this sentence over here. Relative position of the molecules changes with the application of load. Okay? Relative position of the molecule changes with the application of load. That is called deformable body. So that is only we are going to see in this whole strength of material concept. Then to explain about this deformable body, even rigid body behavior in a better way, it has been taken one example here. One fixed support having two rods connected, and one block is at the end is connected. When it is due to that block is heavy weight, and due to that block heavy weight, and it is trying to deform something. Okay, but for block, if you see, for blocks, it is, I would say, it's a displace only, because block is a rigid body, whereas rods are deformable bodies. So that is why rods are getting deformation, whereas black is getting from one place to one place, just displace only. Okay. See, this is the best example and best understanding about the what is meant by displacement and deformation, and where we are, and what is meant by rigid body, what is meant by deformable body. I hope with this discussion up to here, you have been clear the things. What I do, I'll go with the interaction kind of way, so that that will help you people. Someone can speak out whether you are understanding or not what I am explaining. If I am quite fast, please try to inform me. Sir, you are going very faster. We are not able to understanding the concept. What you are exactly trying to say to us. Okay, so that opportunity I can give you. Please, I stopped here. May I know? May I know anyone? Please respond. Students, unmute yourself. Students, please.
Yes, sir, it is understandable.
Is it understandable? Is it understandable? Thank you. Thank you. Yeah, I'm continuing.
Yes, sir.
Yes, sir. Okay.
Yeah, actually, the loads are basically those are external forces. So there is a lot of doubt and even confusion. What is meant by load and what is meant by force? The same only, but forces will be acting on the body in the form of load. That's it. Like when you're simulating any for calculation purpose and for doing any analysis purpose, you will say that this much load is acting. But how this load is acting, the number of the combination of number of forces. The number of forces you are converting it as a load actually. So that is why. So shall we can discuss about the how many types of forces are there. Okay. So there are generally in anywhere if you see there are two type of forces. One is body force and another one is surface force. But sorry, in majority cases that means 90% of cases uh, surface load only we have to consider. So what is meant by surface load and what is meant by body force? So surface force and body force if you see. So first of all, body force is which is distributed over the volume of the body. Okay? So that is nothing but a P equals to gamma into area into L. Okay? Gamma is nothing but a density into A into L is nothing but a volume. So density to volume you will get the unit weight. Correct. So that's all about the body force. Body force means actually inside if any forces are there in the body. So that is we have to take it into consideration. But generally we will try to ignore the self-weight of the members in majority of the cases in this health topic. So that is why only there is a chance of very less chances like 10 up to 10% of chances you have to consider the body forces. Whereas surface forces, whatever I have discussed about like one concentrated force, simply say like uniformly distributed force load or some other uniformly varying load or force. So these all comes under the surface forces actually. Then in this formula, what I have given the body force, this is the full-fledged explanation over here. Length of the component, L equals to length of the component, gamma equals to weight density, that is not per mm cube, and A equals to cross-sectional area, and body weight of the bar for this one, okay, this one thing drawn here, and for the body weight of the bar shall be neglected when bar dimensions are not given. Okay, so this I am assuming it as a like very ignorable thicknesses or some thickness they have given, but they have not mentioned any dimensions. But even in the data also it has been mentioned that ignore the self weight. So that time you must to focus on only what are the other forces or what is the other weights are they coming on the this system. Okay, then come to the for the strength of material point of view, when strength of material you have to implement for the any member, it may be a bar, it may be a beam, it may be a shaft, okay, it may be a rod, anything if you take, if you want to implement the strength of material, there should be there should be some assumptions. What are those assumptions? Means the deformation is elastic. That means it's obeys only Hooke's law. It will not work beyond the inelastic stage. That means the non-linear stage or like after yielding point, whatever the behavior comes in the structural member or structural system or some metal point of view also. So this cannot be valid. Then body weight is neglected, correct? And a member should be prismatic. Okay? Then prismatic means throughout transition of the member there should be same thickness and same weight. It has to be there. Then only it is a prismatic. Otherwise, if it is a varying thickness and varying areas are there, so it cannot be a prismatic. It's a non-prismatic. That is also an assumption. Member should be prismatic. Then only this will applicable. Then member should be homogeneous and isotropic. Homogeneous means throughout the member, the behavior, the elastic constants like Young's modulus, like mu, Poisson's ratios, these are all should be same. If you use the two materials, that cannot be homogeneous. It will not be non-homogeneous, otherwise heterogeneous. Heterogeneous means like concrete is heterogeneous. Correct. So this we are going to apply on the one iron bar, aluminium, like aluminium shaft. So that is throughout same material only. So there is no bronze, brass, okay, like silver. This kind of materials are having the same homogeneous thing. Then isotropic. Isotropic means that is a like metal property. It has like constants are there, like Young's modulus, Poisson's ratio, like section modulus, shear modulus. These are all coming to the isotropic thing. Anisotropic material means it's again going to the non-linear kind of nature. So that please understand prismatic, homogeneous, and isotropic. Once again, I'm pinpointing in that. Of course, I will close this one now, and I will show you the clear picture about the homogeneous and isotropic. It is available in the next another slides. Of course, I will open that and I will try to show that. Let me complete the last assumption, that is load is assumed to be a static load. It's not a dynamic load. Static load, it varies with the only distance, not with the time. Okay. I'm stopping here. Are you able to see this now, Suma? Suma, madam.
Sir.
Are you able to see this my sharing document?
Yes, sir. Strength of materials.
Yeah.
6 to 8. Strength, stiffness.
Yeah. So why I opened this slide actually, I just wanted to explain you in better way what is meant by homogeneous and isotropic and prismatic. Okay. So this is of course another prepared material like running notes and of course handwritten notes. Strength means resistance to failure is called strength. It is a metal property. Like M20 means in concrete actually, for civil students they will understand this. Of course, I am not going into detail in this. And stiffness, resistance against deformation is stiffness. This is a secondary design property. Then come to the assumptions. Metal is continuous. No voids or no cracks. That is called metal is continuous. And metal is homogeneous and isotropic. You can see this. Homogeneous means same. Homo means same. And geneous means origin. So that has, like everywhere throughout, wherever you see same stress, it will not vary one place to another place stress components. For example, it's a wood, iron, gold, steel, brass, bronze, of course, wood, iron, gold, and steel, brass. Bronze not homogeneous actually, but any point in one direction, same property will be there for the homogeneous condition. Okay. Then isotropic. Isotropic means at one point in any direction, same property. That means from one point only that all stresses distribution will be there. So that is called isotropic property. For that example, fine grained material, iron, gold, stress, wood. It's a non-isotropic thing actually. Okay. Then same directional property. That indicates the isotropic. Then orthotropic. Orthotropic means at one point in perpendicular direction, property are different. Okay, you can see the sigma x, sigma y, and sigma z. So perpendicular directional property. This is basically so layered material, wood, sedimentary, rock, marble, graphite, mica. These are all orthotropic property materials. Then you can see here sigma x and sigma x when you're applying axial force. So this will try to like propagate and transfer the stresses in the inside of the body like this. Even for vertically also, if you apply axial load, then this will also show like this. Then now you are pressing the axial stress like in the form of compression. It is in the form of tension. And now you are pressing the same style of the stress, what I can say, behavior and the layers of the stress layers should be same for the same application of the load. So then anisotropic means non-isotropic basically, or allotropic and angioplastic. So what is this means? At one point in different direction, property is different actually. That is actually metal with cracks and voids. Okay, when you have the cracks and all the everything, it will not show the any isotropic behavior. It will go to the anisotropic. That is nothing but a non-linear. Even this is, I can explain you a better way. Once you started testing one shaft or one beam or one rod, up to yield point, it will take the load. Once the yield point comes, there will be a small inside crack or like surface crack, something will happen at yield point. So after that, if you see the behavior of the any material or member, it will go to the fully non-linear and it will go to the peak level. The pre-peak it is okay, but after post-peak response, it will try to degrade very slowly, gradually. So what is the degradation? The degradation is ultimately non-linear behavior that in the post-peak response. Okay. Anyhow, homogeneous plus isotropic, which material it has, iron and copper and gold has the homogeneous and isotropic behavior, and these are like this. At any point in any direction, same property is nothing but homogeneous and isotropic. Now, sulfate neglected. So stress versus strain starts from origin due to this assumption. Okay. Without sulfate, it means it will start from the origin. With the sulfate means it will not from origin. Because of sulfate, the stress already will be there for something, but there is no strain. But after some stress, because why sulfate? Load by area. That load is nothing but already sulfate. So with that load by area, the stress is already started from with some height, some magnitude of the stress. Then it will go like this. So with this, I am stopping here again. I am not going into the detail of again superposition principle. That will come. I will come back again. Okay. So this is all about assumptions. Now, so whatever we have discussed, the forces, body forces or surface forces, then of course, how these forces are becoming into the loads, but how many type of loads are there? If you really see the classification of the loads, how many types of loads are there? Okay, so there are so many category of loads are there. First of all, if you see the with respect to time, if anything is varying or if anything is happening, that is nothing but a load with respect to time. There are two types. Then with respect to direction also there is a load, and with respect to distribution. Okay, this is generally happens in the beams. And now first we start with the with respect to time. So static load, sir. Static load is not time, sir. Static load is not with respect to time only, but which is comes under the category of the with respect to time only. Why it is, I will explain you. Okay. Next, another one is dynamic load. Under the static load, again there are two type of loads, that is dead load and next one is gradually applied load. Okay. Dead load means like if you talk about the mechanical people, if there is a one motor, you are not at all removing that, you are continuously you are keeping that. Otherwise, for keeping the motor with help of the civil engineer, you constructed a one platform, like one big platform to place your engine or machine. So that platform, whatever it is there, you are not going to disturb that for a long time. So that is nothing but a dead load. Even in the buildings, if you come, wall you are constructing for your room closing. So wall is going to be a permanent. So wall is comes under the wall weight is wall load comes under wall weight is comes under the dead load actually. Okay. Then what is meant by gradually applied load, that we will see in the diagrams. Let me move next on dynamic loads. In this impact load and fatigue load. Impact load and fatigue loads are very, very useful for the mechanical people only, even rather than civil people. Dynamic load only the exactly it will vary with the time, because it will happen in very fraction of seconds or very less amount of time. Very fast it will happen. So that is why the dynamic load is only comes under the with respect to time. Static load also indirectly comes under the with respect to time, that I will explain next here. However, the impact load is or sudden applied load. It is nothing but a your shock, like suddenly you are applying. That is impact load. Fatigue load or cyclic load. Fatigue load and cyclic load means especially like if you see the wheel load, if you were talking about any car or any lorry or any bike, it is repeatedly going and running, but it is like a moving load, but it is repeatedly coming like cyclic load, cyclically. Otherwise, if you take any pen stroke or any shaft is there, like even if you take the turbines, there is a one inside, there is a big fan. That Pelton turbine and all. So that one is also having number of times it will rotate like anything. Then that is nothing but a cyclic load. That means cyclic load means at one place repeatedly you are applying the load. That is nothing but a cyclic load. So it is also known as a fatigue load actually. Then with respect to direction, that is first of all normal load and shear load. What is meant by normal load? It is always perpendicular to the cross section. Correct? Say you have a cross section like this. You have a cross section like this. It is a perpendicular to the cross section. Correct? Whereas shear load is parallel to the cross section. Correct? Parallel to the cross section, because you take cross section only, not side view. Side view, if you talk about, I think are you able to see my demo of hand demo? See, this one is longitudinal section. This is lateral section. Correct? So now I am talking about the cross section is this one. This one is cross section for this beam. So along this cross section, you are applying the normal load like this. So this normal load is perpendicular to this cross section only, whereas your shear load is you are applying at the like this. That means it is parallel to cross section only. Correct? It is parallel to cross section only. Sides ka apply cheste avi parallel ga unnattu. Shear vachesi. Ade meer ila straight ga apply chestunaru anukondi. That is normal to the cross section. That is only, please do not confuse here what is meant by normal load and shear load, which are very, very important for conceptual point of view. And my dear students, this subject which I am explaining you, it is not only limited to the GATE examination point of view. Nowadays, for all PSU PSU examinations and for job selection of NTPC or anything you take like government related jobs, so many are there like TCE, Tata Consultancy, Engineering, NPT, Power Grid. These all are taking based on GATE only, with GATE score. So how GATE score you can crack if you are not ready to join in the join for the masters, if you want to do your aspirant of the job, then this subject will help you not only for the GATE preparation, for preparing for the competitive examinations also. Next, under the normal load, you have a axial load and another one is eccentric axial load. So this is basically we used to consider for the bars. And come to the shear load, which is there parallel to the cross section. And in that there are transverse load. Another one is eccentric transverse load. Okay, transverse shear load. TSL means transverse shear load. TSL means transverse shear load. Transverse load, eccentric transverse shear load. So what is meant by transverse load and what is meant by eccentric transverse shear load, you will see in the next discussion. Then come to the, with respect to distribution, there are two types of loads are there. Then one is concentrated. Concentrated means what? Concentrated at one point only, it's nothing but a point load. Okay. Then distributed load. Under the concentrated again, there is a concentration point load and concentration movement. Okay. There will be a movement means maybe at one point there will be one couple like this. Couple. So that is also comes under the concentrated movement actually. Then come to the distributed load. In this, please, whether you are able to see or not, but I can explain you very clearly. This is UDL, this is UVL, and this is UDM. That means uniformly distributed load, uniformly varying load. Nothing but a like triangle load, trapezium loads and all, trapezoidal loads and all. Nothing but a uniformly varying loads actually. Whereas uniformly distributed load means throughout same load only, but it will distribute throughout on the span actually. Then UDM is uniformly distributed movement. Okay, sometimes like a movement also directly. What is the units of movement? A Newton meter. Whereas uniformly varying load, uniformly distributed load, kilonewton per meter. Okay, so uniformly varying load time, you must calculate the equivalent load by taking the formula of the triangle or trapezium. Triangle formula half into B into H, area formula. Trapezium formula A plus B by 2 into H. Like that, you have to consider the equivalent load. You have to apply at the like central distances of the that particular either triangle or trapezium at a particular place, and you have to do the normal calculations. That means whatever the uniformly varying load is there, you can convert into as a point load also. Even UDL also you can convert it as a point load, because what is the units of the UDL? Newton per meter. So Newton per meter, if you multiply with meter, then you are getting Newton only. Newton means the point load only. So like that, please think on this. Then come to the UDM, uniformly distributed movement means movement units are again Newton meter. So Newton meter it has to go means you have to divide it by meter, no? Correct? So whatever the value it has given, if you divide it by meter, then you will getting newtons. Correct? Okay. I'm just facing the breathing problem. Sorry. Yeah, come to the continuity of the loads. If you talk about the static loads first, the first one I have given here, dead load. What is that? Loads of structures, living things, or weight of, sorry, loads of structures are weight of non-living things. Okay, weight of non-living things means on the wall you can't live. Okay, you can't go and sleep on the wall. And loads of structure means especially like this wall load and even slab load. This and all comes under the dead loads only. How the things are there, you see, there is no variation with the time and all. Load will be throughout time. It is constant only. Throughout any time, it is constant only. It is not varying with time. Then gradually applied load. This is also comes under the static load. How gradually applied load comes under the static load means you may say that, sir, this triangle line, that means this inclined line showing as it is varying with time now. Then how you are claiming the this is a static load? Why I am claiming? 1 minute. Hello. Namaste. Then అవునండి, అవునండి, అది ఆ రోజు మాట్లాడారు కదా మీరు. అదే నేను చెప్పానండి, రెస్పెక్టివ్ పీపుల్కి వాళ్ళకి చెప్పాను, చూస్తామన్నారు. మొన్న ఎవరు కాల్ చేశారు? వాళ్ళు ఎవరు? అవునండి, కిషోర్ గారు వేరే వాళ్ళు ఎవరికి చెప్తే చేశారండి. సరే అండి, సరే అండి, పంపించండి. సరే, పంపించండి. మీరు మెయిల్ పెట్టేసేసి నాకు పంపించండి, వాళ్ళకి మెయిల్ పెట్టేసి. అయితే ఓకేనండి, సరిపోతుంది, పెట్టండి. Sorry, I'm extremely sorry. Yeah, urgent call. Yeah, why this is it has taken under the category of static load means, see, when you're applying the gradually load, it is taking long time to It is taking very long time to take this much load actually. So that means I will not call it as a dynamic load. Dynamic load means it's very short time you have to apply the load, or within very short time the load will be applied, like impact load and fatigue loads. With very short period like this, it is a fatigue, and impact load means suddenly there is a touch like this. Okay, so this kind of loads category, which this will not come under. Even it has been written here, to reach its maximum value it is taking considerable amount of time. That is why this is a gradually applied load, comes under the static load. It is not varying with time. Then dynamic load, you can see impact load. See, it has taken very less time, correct? It has taken very less time, whereas this has taken long time here. See, if you draw the straight line up to here, from 0 to here is a very long time. Whereas this one is, in the impact load, if you see, the P is occurring with a very short period of time. The slope is very high. The slope is very high. To reach its maximum value, it is taking very less time, correct? To reach its maximum value, it is taking very less time. That is nothing but an impact load. Then come to the normal load, first of all. Of course, I am not explaining about the fatigue load here, because fatigue load and cyclic load now is not our cup of tea. But as per a classification point of view, it has been shown here. It will come in the, especially for machine design time, when mechanical people are preparing for their gate examination or for general preparation. Their cyclic and fatigue loads will come into major role, play the major role. Then I'm going back to the normal load, that is with respect to direction. Here normal loads means, you can see I have a cross sections of XX, YY and ZZ. Okay, you can see this one. This is YY. Then I have a XX and this is ZZ, correct? So this is looking like a 3D, and when I'm having the P load at this point, P load when I'm applying here, P load when I'm applying here. So this is nothing but a centroidal axis. X-axis is nothing but a centroidal axis, correct? Centroidal axis. You can see this one. This is nothing but a centroidal axis. So X-axis is a horizontal centroidal axis. Horizontal centroidal axis. Whereas YY is nothing but a vertical. You can see this vertical centroidal axis. I can show this. Yeah, you can see, observe my dear students, this X-axis is horizontal centroidal axis, YY means vertical central axis, and opposite to that polar central axis is nothing but a Z axis. So longitudinal axis is nothing but a normal load actually. Okay, longitudinal axis is nothing but a normal load. Okay, so in the normal load means, see, axial load is nothing but a which is along the longitudinal axis. That means if you take the any one bar, if you are applying the any load like this or like this, see, for suppose if I am observing this is XX and this will be ZZ and vertical always YY only. So say now I am applying the P along the XX direction, that is longitudinal axis, that is nothing but a axial load. Then what is meant by eccentric axial load? Whatever I have given in the list actually here. See, in the normal load there are two types. One is axial load and another one is eccentric axial load. So in this eccentric axial load means it is a parallel to longitudinal axis, correct? Parallel to longitudinal axis, but it will not be at the exact center point. It will be parallel to longitudinal axis. See, this is eccentric axial load. This is eccentric axial load. Why? Because from center point to this load, if you see, there will be some eccentricity, but it will be there always parallel to longitudinal axis only. So here P is axial load, Q is nothing but eccentric tensile load, and R is nothing but a eccentric axial compressive load. Correct? Are you agreeing with this? P, Q, R. Here? P, Q, R. Here? So if it is okay, I'll move on to the another categories. Normal loads are very clear. What is meant by axial load and what is meant by eccentric axial, both tensile and compressive loads. So tensile means like this, away from the point. Compression means towards point. Okay. And shear load. So in the shear load, again there is a transverse shear load, that is TSL. This is perpendicular to the longitudinal axis and passes through it. Okay, perpendicular. You can see back. Go to the back. This is perpendicular to this one. This S is there, no, vertically. This is perpendicular to axis. This is x-axis and meaning perpendicular ga nenu x apply chesanu. Okay. Then malli I have applied U parallel to your y-axis, whereas eccentrically perpendicular to x-axis. U, S, T. There are three shear loads has been applied here, but S is exactly perpendicular to x longitudinal axis, and T is again no, T is actually again you can see, you can go here, yeah, perpendicular to the longitudinal axis and passes through it. S is nothing but a vertical TSL, whereas T is nothing but a horizontal TSL. Correct? Horizontal TSL, vertical TSL. But these two are we are applying at the perpendicular to x-axis. Okay, please do not confuse there. You can easily understand that. Eccentric TSL means perpendicular to the longitudinal axis but away from it. It is not going into that point, but these are away from it. The best one is U. What I have shown here, U is nothing but a your eccentric eccentric TSL actually. Eccentric TSL, transverse shear load. Okay. You can do the one example, basic example here. What is that basic example means? There is a one L-shaped beam. We are applying the P load at the A point. A, B, C, D points have been given, and at D point there is a fixed support. At the end, free end point of the A, you have applied the P load. Now the load type and the each and every span, what type of things are there, you can see, you can easily identify that. These kind of problems also will come in the gate. They will give this kind of problem and they will ask you what is there in the DC or what is there in the CD. Okay, you can easily find out load type and what is the AB. The span is AB. In the AB, you have a, due to this P is actually going inside. Due to this one, axial compressive load only will come, correct? Then this P load will be TSL for BC, correct? Because BC is a perpendicular to P. Otherwise, for BC, P load is a not parallel, it's a perpendicular load. So perpendicular load is nothing but a transverse shear load actually, correct? P is acting as a for BC transverse shear load. CD, for CD, P is acting as a eccentric axial tensile force, correct? Correct? It is acting like this, and for CD, it is eccentrically, because the distance of CB is nothing but a eccentric distance, but it is acting axially, but it is acting like a tensile. Okay, tensile. Okay, because when you are pressing this one, this will try to pull out like this. This will try to pull like this, and automatically in CD, the tension will develop. Actually, the tension will develop. So that is why eccentric axial tension load will be there in the CD or DC. Then come to the beams. For beams actually there is a longitudinal axis is along the x-axis only, like along the beam we have a longitudinal axis. But for columns, the vertical axis is a longitudinal axis. And here one example you can see hereafter. For indicating the compressive load, there will be a one cross symbol with rounded symbol. If I show like this, it's a compressive load. If I show the dot with the rounded one, it is a tensile force. Tensile force, compressive force. Okay. So now with that, if you take this one, like P earlier actually have been applied horizontally. Now for suppose P, if you apply vertically like this, okay, vertically like this, what type of loads you can face at the AB? AB actually you will have a TSL, whereas BC eccentric axial tensile force for BC this is, and whereas CD again it is a TSL only. Okay, and in the beams if you see simply supported beam, if you can even cantilever beam. For suppose if you see the reactions, RAH means horizontal reaction, vertical reaction. Of course, this is generally, but you must understand this type of L-shaped one and even different shapes of uh, frames, beams. Okay. Then third one, if you see here, what type of load it is being applying. You can see this. It is nothing but a compressive pre-force, and for AB, like compressive, compressive force for AB, it is a TSL. TSL means transfer shear load, and whereas for BC, it is a eccentric TSL. But eccentricity is equals to AB, whereas for CD, it is a eccentric TSL only, and E is CB. Okay, E is CB. That means eccentricity. This is actually same case of this one only. Okay, same case of this one. How the load has been applied, like a one, compressive force. Then equivalent load under eccentric axial loads. Okay, this is again further discussion of how the now from load to stresses are slowly developing. You can see here. Say I have one cantilever plate or cross section. I am applying the one axial load P1 here and P2 inside. Like P1 is as a tensile and P2 as a inside. And at corner, at bottom of the that member, I am applying as a P. Now, if I go into the side and if I see P is applying like this only, correct? That to dotted line means it's nothing but a tensile only, tensile. And what is the half of that cross section? It's a D by 2, and width of the cross section B, correct? So, whereas if I talk about the P with respect to axis, if I take P into D by 2 is nothing but your bending stress only, it is happening, correct? Your movement only, okay? The movement only it is happening, P into D by 2. So there only you can see here steps. Apply P1 equals to P2 equals to P at the these places, different places which are shown here. Effect of P1 is to cause a axial load P, correct? Effect P and P2 is to cause a bending couple, correct? If you talk about the P with respect to P1, you are making a movement actually. Whereas if you're only talking about the P1 and P2, it is direct. It is direct. Nothing is there. Okay. So here it indicates sigma A is nothing but a axial stress. Sigma B is nothing but a bending stress. So P by A is a direct stress, axial stress. Sigma B is nothing but bending stress means M by ZNA. ZNA means section modulus at the neutral axis. Section modulus at the neutral axis. So M equals to P into D by 2, and ZNA is nothing but ZNA equals to I by Y max. That is 12 PD cube. That is moment of inertia divided by D by 2. You are getting ZNA equals to 1 by 6 into PD square. Correct? So like this way, you can find out the axial stress and bending stress for the given member like this. Okay. Now the shape is not looking like a very simple shape like rectangular or something, but it is looking like a one C kind of shape. That time, how to find out your stresses, top stresses and bottom stresses, how to find out, it has been given here. This kind of problems also will be covered in the gate examination sometimes, but you must remember these concepts in very good way. Okay. So first of all, if you see here, the half of the whole depth of this C section, C shape section, if you see, that will look like from cross sectional point of view, it will look like a rectangular only. But when you come to the side only, it will look like this is original shape of the C. And if I am distributing these all shapes into three shapes and three parts, 1, 2, 3 like this. Okay. So in these three shapes, now how to find out the the sigma top. That means stresses at the top and stresses at the bottom. If you want to find out, you can easily find out by observing like this. Okay, that is now first sigma top equals to, first of all, here you have a sigma A, because where I am applying load, where I am applying load here, where I am applying load here, you can see this P. If small arrow I have applied here. Okay, when I am applying load here at the center in the form of tensile force, so stresses will be developed at the both top and bottom. So first of all, due to this P at the top, you will have a sigma A. Sigma A means axial force. That is P by A area. So what is P by area? Again, area is equals to B into D by 2. Correct? This area only, no? B into D by 2. Yeah, this is the cross section B, and your D by 2 is half of that. Okay. Next, sigma B is equals to M by ZNA. M by ZNA means, again here your the center of the distance is from D by 2 to center of the section is D by 4 actually. So the D by 4 can be taken here. That is P into D by 4 divided by whatever ZNA you can put. Now WB you are getting as a 6P by BD. Okay. Please observe here the where is the P load is getting applying. For suppose I apply the P load here, the whole scenario will change. That means you have to consider the whole height of the member. Okay. So due to this P load effect, where is the effects are coming, you must observe. Then come to the B bottom, sigma bottom equals to, as it is, axial stress will be there, but from here minus sigma B will be there. Sigma B means that is bending stress. Why minus? Because minus it is there because downward part of the part, below the neutral axis of the part, this will be, you have to consider as a minus WB. So with that, sigma top and sigma bottom, when you get these applications like this, and when you have the expressions sigma A and sigma B, then easily find out the sigma top and sigma bottom like this. Okay. Then for suppose load you are not applying as a tensile force, you are applying as a compression force, then the shifting you can see here first of all. Okay. Sigma top, first of all, here it is already minus sigma it will be because of compression, and here also minus sigma A because of compression. But due to this application of the reversal application of the load, the minus portion will go to the top of the sigma B, and plus portion will come into bottom, that is sigma B. That is sigma B means, please assume that it's a bending stress. So that's all about the axial stresses and bending stresses. How it will be, those are varying. Okay. So with that, so again sigma top, sigma bottom, how it is varying, you can see. This one actually very, very important for both mechanical and civil people. How the forces we are applying and where it is happening, the normal stress and bending stress, you must observe, and based on that you have to calculate the all the formulas, and immediately if they ask to find out anything by keeping this expression, you can easily find out the respective stresses at the different level. Now simple stresses and strains, if you see whatever I shown, that one earlier, the same concept it is explained here. The load has been applied here like compression load only, sorry, what I can say, yeah, compression load only. So based on that, these all formulas has come into picture. Then come to the another one, stresses at point A and B. Stress at point A and B, this actually gate question actually. There is a one L-shaped section. Dehydration effect. Sorry. Yeah, you can see this one. Here you have a cross section of 0.5a, 0.5a half of that one, and the total is 5.5a. Then for this, how to find out the sigma a equals to that is a both combination of axial and bending stress actually. So here, as you know, area is a square and the sigma a is directly p by a square, and sigma b equals to m by ZA, m equals to p into e, whereas ZNA equals to half into a cube only, no? 1 by 6 into a cube. So based on that, if you find out sigma b also, you are getting it. And again, top one is like that maximum one is sigma a plus sigma b, and whereas sigma b is downward one is sigma a minus sigma b. Okay, why this is happened? Because of this is tensile force. We are applying it. You can see this one. This is the force. Correct? At the top, I have been applied. But when I'm applying the top, this effect will be there in these two both shapes. This is vertical shape and this is horizontal shape. Now, based on that, this is a replication of the previous problem which I have been explained, that you understand. Okay, top applied, but it is not. If it is applied this load at here, again the system will be same. Like sigma a plus sigma b will be the same only. Even sigma a minus sigma will be different, but the formulas will change here because this may not be fully area. You have to consider even this one. You have to take 0.5a. You have to consider because half of the portion only this effect will be there. Like that, you have to just to play the role. Okay. And here, if you see why p into 5a it has been put here because this is total 5.5a, whereas this one is 5a only, no? So up to center, it has been taken as a movement p into e. So e here is 5 into a, correct? Please understand that. And based on that, sigma b and sigma a can be calculated, and finally you can show the expression. This is the answer for this problem. Okay, this kind of problems also repeatedly they are asking. Please focus on this. And for the given cross section, determine ratio of maximum tensile stress to axial stress. R equals to maximum tensile stress by axial stress. One minute a day. We have completed 1 hour, 10 minutes. We have completed. We have started at 11:30. Now it is 1:44. Yeah. Now there is a one cross section, like one square cross section, having the dimensions of vertically 50-50 altogether 100, and horizontally say it is 200. Maybe it's a rectangular shape one. Yeah, and it is been applied at along the y-axis from x-axis with the eccentricity of 25 magnitude or 25 mm, we can say, in the form of tensile load. Correct? Dot means tensile load. P equals to 200 kilonewtons. How sigma top it is going to be? Sigma top is going to be a sigma max. Why sigma max? Because the load is nearer to top portion only. Wherever the load is very nearer to so and so portion, there only will get maximum stress. For suppose load is at the very near to bottom portion, there only will get the maximum stress. So that is why I am telling this one. So sigma A as it is plus sigma B, because of sigma B, why it has come the top portion, and again sigma bottom, again sigma A minus sigma B. That same case as it is earlier case, like you can see this one, I-shaped case. Okay, sorry, C-shaped case. So here you can how to calculate this sigma A plus sigma B. You can calculate with the 25 MPa with the formulas this one. Therefore, sigma A equals to 200 into 10 to the power of 3, and area you can put 10 MPa you are getting here, and sigma B M equals to P into E. your P coming, and again here sigma B can be calculated to 15 MPa. So altogether 10 plus 15, 15 MPa, 25 MPa, and sigma A is already here 10, and sigma B is 15. That is why it is coming minus 5 MPa. And sigma XX, it is actually half BD square. Why you have to find out the sigma XX? Because if you are applying the load at the y-axis, you have to find out the z at the x-axis. For suppose you are applying the load on the x-axis, you have to find out the z at y-axis. That vice versa, you know. That is why I showed you example. I have written an example. That means you are changing the load here. You don't need to confuse. Only you have to matter of changing the z-axis calculations only for finding the m, for finding the sigma b. Okay. So based on this, you can easily find out the ratio of that one also. What is meant by maximum tensile stress and axial stress. Then I am moving on to the another one. Determine maximum value of eccentricity such that there should be no tensile stress in the member. There should be no tensile stress in the member. So this is the one problem. It has been given like a load is applying here like a cross section load. This is like a compressive load in the periphery, in the inside of the one circle. Now when you are applying the load here, obviously this side I have a sigma right. Sigma right means stress in right portion, and left side I have a sigma left. Then obviously it's a compressive force. Compressive force means first of all I must take the minus sigma a, and obviously my load is nearer to this side. Then I have to consider this is as a minus sigma b. That is minus bending stress, and here plus bending stress will come. But here it should not be positive actually always, because it should not be positive. Why? Because if it is positive, then there may be a chance of the cross section may break. There may be a chance of the cross section may deflect or twist. So that is why this portion should not be positive. So this is condition for this case, and you can see the sigma left and sigma right, how it has been taken from the previous discussion. I hope you understood this. I don't know. Actually, I am thinking that. Hello. Sorry, Suma. Can you respond on this?
Hello, sir. Cheppan, sir.
Yeah, actually, I'm thinking if someone calling, whether I am audible or not, or someone by taking my number, they are calling. Sorry, you are not audible. Please cross check your audio system or something. For the purpose only, someone is calling like that. I'm assuming.
No,
So
sir. You are audible, sir.
If anything, if any technical problems are there, immediately please correct me, Suma.
Okay, sir. Okay.
Okay. Yeah. Next, sigma A equals to P by A area. That is pi d square by 4. No, pi d square by 4 is nothing but a 4p by pi d square. So sigma p is m by zna, pe by zna again. For zna, for a circular section, pi d cube by 32 pe. Then 4p by pi d square is a condition less than or equals to 32 pe by pi d cube. So from here, if you cancel everything, d by 8 less than or equals to e. So that means this eccentricity from center should be less than d by 8 actually. Okay, this area, this portion is d by 8. So in this region only this load has to apply. So this is very important for designing of the shafts, even for designing of the any rotating elements. If you are fixing the eccentricity within that limit, it will not happen anything. If you are going beyond that, then the orbit will not be under your control, and there is a sudden breakage or breakdown of the machine. So from that, E max by E theoretical, if you calculate 1 by 4, it is coming. It is nothing but a 1/4 middle rule. So middle rule point of view, this one you have to be very careful. This is especially for square, rectangle, circular, triangles purpose. We can use this. Okay, this middle third rules. These are very, very important. Middle third rule. Then next, ZNA equals to INA plus Imax for circle. Even ZB equals to sigma B equals to, this is the formula which I have already shown here. Then I'm moving on to the next one. Yeah. Next is stress. So stress means what? Even they used to ask the interviews sometimes. What they will start, they will ask you to introduce yourself first with your introduction, small introduction, where you from and what are the degrees you have been completed, what are the credits of yours, and what is your percentage and all. After explaining this, introducing yourself, your interest and everything, and they will ask you. I start with basic questions. Are you strong in that? Yeah, you will say yes, sir, yes, sir. First, they will ask, what is meant by stress? If you say load by area, first itself they will send you out from the interview panel. You should not say stress is a load by area. You must explain stress is nothing but an internal resistance offered by a body under deformation caused due to loads. And that too, stress is a tensor quantity. Okay, stress cannot be a scalar quantity or vector quantity. Stress is a tensor quantity because tensor means it has two directions, x and y. Okay, two directions. Scalar means what? Zero order tensor, correct? Vector means first order tensor. First order tensor, that means only one direction will be there and one magnitude. Whereas stress is having two directions. So stress is defined as the intensity or magnitude of an internal resistance force against the deformation caused due to load. Difference between stress and pressure. These are very important points. I will read out and I will try to explain this. Pressure is the magnitude of external force acting or applied at a point, whereas stress is internal resisting force. Okay? Pressure always acts normal to the surface. Pressure is always act to the normal to the surface, whereas stress may act perpendicular or parallel to the cross section. Perpendicular undochu, parallel ga undochu stress. Magnitude of pressure at a point in all the directions are equal, whereas stress magnitude at a point in all directions need not to be equal. It may vary. Due to pressure, stress is developed. ఎందుకంటే ఇక్కడ మెయిన్గా స్ట్రెస్ ప్రెషర్ కి ఎందుకు డిఫరెన్స్ పర్టికులర్ మనం మాట్లాడుతున్నాం అంటే, బికాస్ స్ట్రెస్ ప్రెషర్ యూనిట్స్ ఆర్ సేమ్, న్యూటన్ పర్ ఎంఎం, మీటర్ స్క్వేర్ ఆర్ ఎంఎం స్క్వేర్ ఉంది, కరెక్ట్? Actually, I'm extremely sorry because I should not eat like this in between while taking the GATE classes because it's a very official forum. But please excuse me extremely because I'm not feeling well due to this corona period. Some dehydration and I'm getting suffocating and breathing levels also are not appropriate level. But why still I'm taking classes means I have committed and it is been planned everything, so I don't want to disturb the schedule. So without out of my capability, I am taking these classes. Please excuse me. I'm really requesting you all. So that's why actually stress and strain, both units are same, but there is a slight difference in the stress and pressure. That is why these all points has been included and better understanding about the pressure. See, due to pressure, stress is developed. But due to stress, pressure is not developed. Okay. Measuring instruments are there for pressure, but not for stress measurement. Stress ki measure cheyadaniki instruments undavu. Endukante nenu cheppinattuga deformation strain vastundi, strain nunchi యంగ్స్ మోడల్ అలా మీకు రివర్స్ వే లో రావాల్సిందే, కానీ you can't measure stress directly by using any tools or instruments. Stress is a second order tensor, whereas pressure is a scalar quantity. Okay, pressure is a scalar quantity. That means it is typically zero order tensor. And the stress you can see here in the better way when you are applying the two loads in the form of tensile forces. When you cut it here, how the pressure is you can see different types of stresses here. So P is a pressure. Now you are applying P pressure, and due to this P, your stress is developing along the cross section of the member. That's the this point is indicating. Due to pressure, stress is developed, but due to stress, pressure is not developed. So okay, F equals to total internal resting force offered by the plane of cross section of the bar. Okay, so here sigma limit delta A tends to 0. So therefore, delta F means change in force by change in area. This is the real definition of the stress actually. So therefore, now if you integrating the change in force equals to because I am taking into that one whatever denominator is there, I am taking into another equal side. Now you can apply the integration because this change in force means very small quantity, the infinitesimal quantity. So from that infinitesimal quantity, if you want to bring out that unknown things, you have to do the integration. No. So what is the physical meaning of the integration? The integration means you are refining the problem. You are defining the error. That means df means it has some error or it has some problem. So that error you are reducing and you are bringing it to the original form or accurate form. That is why you will apply the integration. But as of now, maybe you are in final year or you may be in third year, you might have know about the integration in the even when you are plus 2 also you utilized the integration and differentiation. But there are so many people. What is the exact physical meaning of the integration and differentiation? So many people don't know. They may think that only integration means integration means that x plus 1 in the power and integration operator will come like plus dA something. No, it's not that. It is a physical meaning of reducing the error in the one problem or one such system. Okay, so here actually it's the actual definition of the stress as I shown you. Okay, sigma equals to delta F by delta A, but actually you learn F by A. That is invalid. I am telling you. Stress equals to load by area. If you say that is only will applicable up to one dimensional. If you want to go with the 2-dimensional, even 3-dimensional, this P by A is not at all valid. In 2-dimensional means what are the things will come stress point of view? Sigma xx, sigma xy, sigma yx, sigma yy. 4 components will come. There is nothing but a plane stress problem. Then if you go to the 3D, there is nothing but a stress tensor. 3-dimensional stress tensor. Then you will get 3 normal stresses, 6 shear stresses. Whatever the sides are there, those are shear stresses. Whatever the diagonal one is there, it's nothing but normal stresses. Normal stresses means along the longitudinal direction you are applying the force. Due to that one cross section, if you take wherever due to that force, whatever the area is affecting, that is only how to take. That this concept you must understand with even C type of thing we explained, and one rectangular shape we explained, one L shape one we explained. That you think when you apply load and this load, how much area it is affecting and what area only have to consider. Due to that load, top stress is what, bottom stress is what, whether stress is throughout is same. Why stress is throughout is not same in the previous cases? Because those shapes are not in regular shapes. L shape, maybe size is same only, but shapes are regular shapes, not regular shapes. So that is why you think that which type of load, compression load or tensile load, and where you are applying and how the stresses are coming into the picture. Then integration when you apply into the df and this one, and this will become f. Of course, sigma you cannot apply integration because it's a, as I told you, it's a tensor quantity, so you can't do that. Then you have to integrate this dA formula, this one operator. Then this will become 1, correct? So therefore, f equals to sigma 1 into a, correct? This will become a sigma into a. So therefore, f equals to sigma a. Then sigma equals to f by a. From here only it has come everything. Okay. Then sigma is uniformly distributed over the cross section of the bar, or sigma is constant. stress always develops in the direction of applied load. చూడండి ఈ డెఫినేషన్ కూడా వెరీ ఇంపార్టెంట్. స్ట్రెస్ ఆల్వేస్ డెవలప్స్ ఇన్ ది డైరెక్షన్ ఆఫ్ అప్లైడ్ లోడ్. స్ట్రెస్ స్ట్రెయిన్, లోడ్ డిఫ్లెక్షన్, స్ట్రెయిన్ స్ట్రెస్, సేమ్ సైకిల్. ఇప్పుడు నేను when I'm applying any load, I'm just pressing with two sides P load, and this will try to bulge. Okay, and this is a one figure, and again I'm doing here, but I kept some plates over here, some metal, another metal over here. What is happening? Whenever strain or deformation occurs freely in any direction, then stress developed in that direction is zero. Okay, that means for suppose you applied the load, and this is very easily deforming in the direction, but the stress will be very light and zero. Okay, that means wherever the this is only the meaning, no? Whenever strain or deformation occurs freely in any direction, then stress develop in the direction is zero. That means strain గానీ డిఫార్మేషన్ కానీ ఫ్రీగా అవుతుంది అనుకోండి, స్ట్రెస్ అక్కడ తగ్గిపోతుంది. అది మీకు అండర్స్టాండింగ్ చేసుకోవాలి. ఎలాగా నేను దాన్ని ఫిజికల్ కూడా ఎక్స్ప్లెయిన్ చేస్తాను. ఫర్ సపోజ్ యువర్ ఫీలింగ్ సో బటన్ లైక్ స్ట్రెయిన్ అవుతా ఉన్నారు, మీరు స్ట్రెయిన్ అవుతా ఉంటే దట్ ఈస్ నథింగ్ బట్ ఫిజికల్కి సంబంధించింది. అక్కడ స్ట్రెస్ ఎందుకు ఉంటుంది? సి యువర్ body is very strong, but you are feeling stress is like a mental thing. Okay, so that is why please assume that wherever deformation or strain is occurring very freely, there is no gap, there is no chance or scope for the stress for much scope. That is, there is no resisting force against the deformation. డిఫార్మేషన్ అవుతా ఉంటే దానికి రెసిస్టెన్స్ ఫోర్సింగ్ ఏముంటుంది, ఎలో చేస్తా ఉంది మెటీరియల్. ఫర్ సపోజ్ యూ టేక్ వన్ ఫ్లెక్సిబుల్ మెటీరియల్ అంటే యు ఆర్ అప్లైయింగ్ సమ్ లోడ్ and it is getting deflecting. Where is the resisting force from the inside? There is no resisting force, there is no limitation, there is no control on that. Like if you talk about the controlling board, if you say something to people, your kids or some childs, if they are listening, it's a control, because they are not deforming, or they are not like easily getting strain. They are very strong. So like that you think, and you try to assume this concept, what is meant by stress and strain concept. Then come to the types of stresses. First of all, whatever the normal load was there, and into that normal stress, it is a perpendicular to the cross section, normal stress. Shear stress means parallel to the cross section. Under the normal stress, again we have a axial stress and bending stress. Axial stress is plus or minus P by A, and bending stress plus or minus M by Z, and shear stress, direct shear stress and torsional shear stress. Correct? And under the both axial stress and bending stress, again this will be a tensile axial, compressive axial ayindochu. We have the tensile bending, compressive bending ayindochu. Okay, so like that, these are the types of stresses. Then come to the types of strains. Again, normal strain, epsilon, shear strain, gamma. Under the normal strain, again you have a Langmuir strain, lateral strain, volumetric strain. So lateral strain is nothing but a transverse strain, volumetric strain is nothing but a dilation and depression. And again, these all three are again maybe a tensile or compressive. That means tensile longitudinal strain, compressive longitudinal strain, tensile lateral strain or compressive lateral strain, tensile volumetric strain or compressive volumetric strain. That is the meaning of showing like this. Okay, under the category of normal strain. When then come to the shear strain, straight away there is no anything gamma, and normal strain equal to change in dimension by original dimension. So it may be a tensile or it may be a compression. But here we have taken tensile as a plus, and here it is taken as a minus. Some people, they may follow compressive as a plus and tensile as a minus. That is up to you. Only negative only will change, come interchanges. Everything is reverse. Longitudinal strain. It is the normal strain in the direction of applied load. Lateral strain. It is the normal strain in a direction which is perpendicular to the applied load. Longitudinal and lateral strains are opposite in nature. Under triaxial loading, total 9 strains are developed in the number. in the member. That is 3 longitudinal and 6 lateral strains. Are you getting my point? Under triangle loading, so triaxial testing, triaxial loading, total 9 strains are developed in the member. That is 3 longitudinal strains and 6 lateral strains. Okay, you can see this one. So when you apply the load and this is trying to deform L0 and LF, therefore epsilon x equals to epsilon longitudinal delta L by L0. Delta L అంటే ఇదండి ఈ చిన్నది. So L0 is nothing but delta L is nothing but LF minus L0 then by L0. So this is the formula, and epsilon y equals to epsilon z is nothing but epsilon lateral, that is along the dimensional depth, delta d by d naught equals to df by within 20 minutes, df minus d naught by d naught. Okay, so likewise even epsilon v, the volumetric strain, if you see delta v by v naught and vf minus v naught by v naught. Okay, I hope you understood these all things. Therefore volumetric strain equals to epsilon x plus epsilon y plus epsilon z. Okay, so this has been discussed over. I think I'm moving on to the another discussion. Yeah, superposition principle. And next, superposition principle. So superposition principle means whatever the loads you apply on the any member, like it may be a simply supported beam, cantilever beam, or simply supported shaft or cantilever shaft, whatever you take, it's a beam or shaft, it doesn't matter, because it's a common subject for both mechanical and civil. Even there are so many common courses for civil and mechanical, like engineering mechanics 1 and 2, strength of material, like another solid mechanics, structural dynamics, FEM, finite element analysis. These are all like so many common courses are there for the civil and mechanical. So what is the concept behind over here in the superposition principle is means whatever the load is given on the member, like it may be a concentrated load, it may be a uniformly varying load, it may be a couple, that means movement at one point, concentrated movement. All together you have to include on your beam. Okay, algebraic sum of various effects is equal to the total effect. It is nothing but a superposition principle is valid. Then only superposition principle is valid actually. Then limitation of superposition principle. Linear elastic members only it will applicable. Like Robert Hooke's law is valid. Loads must be up to like this one only. What I can say, elastic limit only. Okay, that means up to the plastic limit it will go, no, because plastic limit means what? Loads will go to the plastic limit and it will not come back to the vertical shape. Okay, so PL means it's a plastic limit, but before that and all everything is a elastic limit. So deformations are very small and not valid for deep beams. This superposition principle will not be valid for deep beams. What are the deep beams? The depth of the beam is more than 750 mm. That comes under deep beam. In deep beams, torsion develops due to loading, which causes deterioration in shape. Okay, deterioration in shape means like it will disturb the whole shape, like cracks will come like that. Shrinking of supports, axis gets curved, distorted. That means due to sinking of support, there is a displacement, not deformation, displacement in the at one supports. Then long columns. Long columns always go with the buckling. Then torsion of circular shaft. Shape remains circular and the shape gets distorted due to this twisting movements. That is called torsion of circular shafts. Then Saint-Venant's principle is valid. Sudden change in any parameter causes stress concentrated. Okay, that means you can see here what is Saint-Venant's principle is valid. For suppose any sudden change in any parameter causes like any crack is occurring, like the shape of the member is also suddenly changing. No, because here something is difference is there and it is changing suddenly, varying. So like this, if any effects will come and this principle will be valid. And stress equals to, as I told you already, the internal resistance developed against deformation per unit area is called stress. Sigma equals to resisting force by unit area. And when you apply the force like this, unit of stress equals to 1 meter square, Kp equals to everything, as I shown you. And sigma fx equals to 0, that is for P equals to R, whereas sigma x equals to 0, P equals to R, and sigma equals to P by A, R equals to R by A. Okay. Note, a member free to deform without showing reaction or resistance will have zero stress, as I already explained. A member free to move away without any frictional resistance, stress developed is zero. A member free to expand or contract due to temperature change, there will be no stress. చూడండి, స్ట్రెస్ ఎన్ని కేసులలో ఉండదో. This is very important. These 3 points are very, very important. Last point is also, of course, is very much important because we will get confused in this case. A member free to expand or contract due to temperature change, there will be no stress. Classification of stress, as I shown you. Classification: normal, direct, indirect, shear, direct, indirect. Okay. Strains: normal strain due to normal force, like shear strain due to shear force, angular change or distortion between any two mutually perpendicular planes in the radiance in shear strain. Okay, ఇది యాక్చువల్గా theta ఉంటుంది కదా, theta is nothing but a shear strain actually. So volumetric strain is due to normal force equals to epsilon v equals to delta v by v, no unit. So normal forces can cause change in dimensions as well as volume. Shear forces can change the shape without change in volume. Are you getting my point? Normal forces can cause change in dimensions as well as volume. Shear force can change the shape without change in volume. External force, deformation, resistance, stress. Deformation interlinking వచ్చి strain అన్నమాట. Strain is independent, whereas stress is depends on strain. Metal properties. Elasticity, ability to regain shape and removal of external force. Plasticity, member undergoes permanent or plastic deformation at constant load. Ductility, material can be made into thin wires. All soft metals like aluminum, steel and all. Ductility is related to tension. Ductile materials are strong in tension and weak in shear. They are moderate in compression. Malleability, pressed into thin sheets. Example, all ductile materials. Properties of malleability and ductile are the same. Malleate means malleability. It's related to compression. Brittle, fails suddenly. Cast iron, concrete, glass all comes under the brittle nature. All brittle metals are strong in compression and weak in tension and moderate in shear. Creep, the plastic or permanent deformation due to constant load with time. Stress strain curves. Low carbon steels, mild steel, that is Fe250. Carbon less than or equals to 0.15%. Carbon is the strength parameter. Manganese is the increases toughness, resistance to impact loading. And strain gauges, extension meter and gauge strength, gauge length. That means while testing the bar, you have to use the strain gauges and gauge length. This gauge length can be calculated by using the empirical expression. This is universal testing machine. Under the universal testing machine, we will test the mild steel. So like that, how to find out the strain and stress from the practical, you can see. ATM can be used for measuring shear, torsion, compression, flexure, tension, torsion, etc. and called as universal. Gauge length is independent of length of bar, shape of cross section, rate of loading. UTM is strain oriented. Resistance offered by the bar is given by load dial. Understood? UTM is strain oriented. Resistance offered by the bar is given by load dial. Strain equals to delta gauge length by gauge length. Correct. Gauge length means whatever you fixed it, and change in gauge length by vertical length is nothing but a strain. So from there, sigma equals to load by area. Load dial leading. Load is dial leading, and sigma is nominal stress or initial stress or engineering stress. Yeah, true stress or instantaneous or actual stress equals to sigma naught equals to P by A naught. A naught equals to true or instantaneous or actual area. Okay. And this is the typical load versus stress versus strain diagram for the mild steel. Like yield strain is there. In the yield strain only, why this proof strain has come means because there is no exact point to find out the yield point actually to draw, because that curve will be like a shaped curve. To find out that exact point, there will be one tangent has been drawn towards to the x-axis. Wherever the touching the point, and that point only they have taken it as a your yield point actually. So for that purpose only the proof strain has come into picture. Proof strain also, so many people will get confused. What do you mean by proof strain? So that is always 2%, 0.2% of the strain only will be there. Then proportionality limit means up to a sigma epsilon, and sigma is proportional to epsilon. Okay, OA is a straight line, and OA is a linear elastic line. Linear elastic line, and Hooke's law is valid up to proportionality limit only. And plastic limit is nothing but elastic limit is nothing but EL is up to B. And A to B is graph is slightly curved. A to B is graph is slightly curved. And Hooke's law not valid in the AB actually. It's a non-linear elastic zone. And loading beyond elastic limit causes permanent set or plastic deformation or residual strain in the material. C is upper yield point. At the yield point, resistance of the material suddenly drops down, which occurs at a strain of 0.002 in most of the metals. The epsilon yield equals to 0.002 value. Okay, and D equals to lower yield point, and DE equals to plastic zone and permanent deformation. In plastic zone, reorientation of molecules occur due to this material becomes nearly homogeneous and start resisting the loading. F equals to ultimate load, ultimate point, and ultimate stress. G equals to brittle point and brittle stress. Okay. Zones: OA equals to linear elastic zone, AB equals to non-linear elastic zone, CD equals to yield zone, and whereas DE equals to plastic zone, and EF is the strain hardening zone. FG is necking zone or strain softening zone. In strain hardening zone, material undergoes higher strains to resist little external forces. Lower yield point D is the design stress in all these designs, like working stress method, plastic theory, ultimate load method, Lewis state method, etc. It is the yield stress corresponding to D. The position of upper yielding point is not stable, which may change based on shape and size of specimen used. Lower yield point is preferred in design. Ductility factor is nothing but a E fail by E yield. For mild steel, BF is 200 to 250 actually. Okay, and high carbon steel also there. Carbon increases strength and hardness, but decreases ductility. And toughness. Toughness means area under the curve. Okay, and example HVSD Fe415 Fe500 not used nowadays. TMT 415 Fe500 used widely and TMT means thermomechanically treated bars, outer surface, and resistant to corrosion, soft and ductile inside. Manganese increases toughness. Proof stress or yield stress, it is the stress corresponding to fixed strain 0.2 percentage is called proof stress. It is used when exact yield stress is not known. It is obtained by offset method. FY equal to yield or proof stress zones. OA equals to linear elastic. Hooke's law is valid. AB is non-linear elastic. Hooke's law is not valid. BC is strain hardening zone. So brittle metal is nothing but a stronger in compression, but moderate in shear, weak in tension. Concrete, cast iron, glass comes under the brittle nature. Brittle metals are tested in compression, whereas ductile metals are tested in tension. Okay. So with this, I'm closing here, and I'm moving on to the few gate-oriented solved problems on the theory of 1 mark and 2 marks questions, because we are running out of time. So I think within 10 minutes I may wind up the things. If I'm not able to cover the full questions in the next week class, I'll try to take again some part from this, and I'll go with the next new topic of the complex stresses. Okay. So I hope what is meant by simple stresses, how the stresses and everything is getting developing. I hope you are understanding it. So with this, the principle of superposition is made use of in structural computations when you can read this, but the answer is B. The changes in geometry of the structure during the application of the loads is too small, and strains in the structure are directly proportional to the corresponding stresses. That is what I shown you. And the maximum value of Poisson ratio for an elastic metal is actually answer is 0.5. For this explanation is also there. Let us see what is the explanation for the question number 2 means. Generally, for all engineering materials, maximum Poisson ratio is it will vary from 0 to 0.5 actually. In between only for the different materials, Poisson ratio will be there. What is the formula for the Poisson ratio? Lateral strain by longitudinal strain. The cantilever beam of tubular section consists of two materials, copper as outer cylinder and steel as inner cylinder. It is subjected to a temperature rise of 20 degrees and alpha copper greater than alpha steel. The stresses developed in the tubes will be compression in steel and tension in copper, tension in steel and compression in copper, and no stress in both. This is also B actually. Why B means tension in steel and compression in copper. Okay, because it is being mentioned here the temperature. The temperature is more in copper actually. You can see this temperature more in copper and less in steel. So due to that, so tension will develop in steel and compression will be developed in copper. Then come to the linear elastic structural element. Stiffness is directly proportional to flexibility. Stiffness is inversely proportional to flexibility, and stiffness is equal to flexibility. Okay. Actually, if this question is not related to like anyone like mechanical people and all, you don't need to refer. I just showing only examples what kind of nature of questions they may ask on our discussion. But your preparation should be like this. Please try to collect a good material like previous solid question papers, and one time please refer the full concept which I shown you, like what mean by stress and how the things are varying and all, and try to solve your own, especially small solid questions only. This type of theory questions are very less they will ask in the GATE exam. So, this is taken from different GATE years, GATE 98, GATE 91, 91, older, too much older. Okay. But still, you may expect any question from anywhere, from GATE when it started, from then any question they may cover, because you can't expect what kind of question they are going to ask. But majority of the questions as per the strategic plan, and observation. Majority of the questions in the gate they will ask like you have to use the calculator. That too, in online examination, normal calculators they won't allow. Virtual calculator you must practice. So that virtual calculator, how to utilize, you have to practice. See, so for suppose sin theta cos theta 60 comes to means it's okay. But integration differentiation comes to means that time calculator how to use you must know. And sometimes denominator numerator will be very higher values like power values will come. That time how to use that we have done all practice. Okay. Then the stress and strain diagram for two materials A and B is given below. Okay. The following statements are made based on this diagram. Metal A is more brittle than metal B. How will decide brittle and ductile? How will decide brittle and ductile? I'll tell you the one example. If metal is a very ductile material, delta U by delta Y. Delta U means maximum strain or ultimate displacement by yield displacement. See here, in this B only the, I would say, more ductile one, whereas compared to the A. Correct? Because A is actually suddenly failed. Up to here only it is taken load and it is failed. But this fellow, it has given some jerk here, but it is going, keep on going. So that means a lot of ductile nature is there for that. It is not a brittle one. So in that grounds, you must choose the answers. So 5 actually, it's a C. Let's see. With reference to the above statements, which of the following applies? C. 1 is true and but 2 is false. Only, no? 1 is true and 2 is false. Okay. So like that, you have to be very careful while understanding the concept. Then pick in a incorrect statement from the following 4 statements. On the plane which carries maximum normal stress, the shear stress is 0. Principal planes are mutually orthogonal. On the plane which carries maximum shear stress, the stress is 0. Okay. So 6th one is again it's a C. On the plane which carries maximum shear stress, the normal stress is 0. Correct. Wherever the maximum shear stress is there, there will be a normal stress is 0. And the shear modulus of velocity, these are all like relations. Okay. And which is covering GATE 2002. Like Poisson's ratio means what? Lateral strain by angular strain. Okay. Like that, lateral strain by angular strain, axial strain. Lateral strain by axial strain. Nothing but a lateral strain by angular strain. So B is the correct answer for 10th. Then the number of independent elastic constants for a linear elastic isotropic and homogeneous metal is how many? B. 9 is 9 is C. What is that? Isotropic and homogeneous two constants means one is Poisson ratio and Young's modulus. Okay. So like that, this kind of direct questions also will help you to get the good marks. But you should not confuse here. With the concept only you must remember, and a few things like with by hearted way you must remember, and you have to get the good marks here. Okay. And come to the 11th question, actually it is a like a direct not a given options, actually it has given directly. You have to find out the value, and this is actually around I think 15 mm. The tapered circular rod of diameter varying from 20 mm to 10 mm is connected to another uniform circular rod of diameter 10 mm as shown in the following figure. Both bars are made of same material with modulus of velocity when subject to a load P. The deflection at A is how much? Okay. Then elastic bar of length. So like this kind of this is actually 2 mark question, and this is also 2 mark question. Sorry, this is one mark question, and this is also 1 mark question. But it may give like one fear to you, but you don't need to fear. If you really observe the problem keenly, everything is there inside only. Okay. Then come to the 2 mark questions. So this is a little bit lengthy, so you must use this some rough work for applying the two lines. So this is directly it is asking. It is the addition of both two AE is there, A is there. So likewise, for 2 marks questions also we can find out the answers. Okay, then we'll move on to the first of all explanations, but these are questions are there. There are explanations. You can see. For one more question, answer it has been given B. What is why superposition principle is applicable for certain numbers with negligible deformation, loads acting are within proportionality limit. That is why it is valid. Next B. The range of Poisson ratio for engineering materials is ranging from 0 to 0.5 only. Then next question number 3 also B. Steel is less active due to temperature changes compared to copper. Therefore, steel is subjected to tension and copper is subjected to compression due to composite action. Okay, that is also understandable. Then next fourth also B. For any linear elastic members, stiffness is reciprocal of flexibility. Okay, and C. Metal A is having lesser strain at failure because A is brittle. Obviously, that is only we discussed. Then C. On the plane of maximum shear stress, normal stress any may also, which is sigma average equal to sigma 1 by sigma 2 exists. The most appropriate answer is C. And answer A, answer 7 answer, 7th question answer A. This is the expression. B, expression of this. And for C is for homogeneous isotropic materials, independent elastic constants are 2, E and mu, Young's modulus and Poisson ratio. And Poisson ratio formula. And this is the formula for 11th question. Then 12th question, 11th, 13. Then come to the 2 marks question. PL by AE, PL by 2 AE. Directly we will get 1.5 PL by AE. That is answer C. For the second in the 2 marks second question is PL by AE and PL by 2 AE and PL by AE. Like that, if you add everything, 2.5 PL by AE. Then and this kind of another questions like free body diagrams you have to draw, and we have to find out the sigma 1 and sigma 2 directly, like P by A like that. And finally, sigma max is 25 only. Out of that, you have to show the maximum value. Then sigma equals to alpha into D means it's like a thermal stresses. Then this is of course this is like from again stress and strain formulas only. Then this is also one trust kind of thing. Of course, a little bit lengthy. Heavy lengthy things I would say you can skip because if you skip this one, another thing may help you like in another subject. But better, very easy things you try to concentrate, but very tactics way, like very strategical way you have to plan. Blindly preparing much and when you move to the examination, not remembering anything, not like that. You have to be show like a very smartism. Smartly how to write the exam. You should not fear first. Your mind should be very clean and fearless. You should not attempt and to select the native marking. Once you select the native marking, your total preparation, your total hard work will go somewhere. Okay, so be careful. Thank you, one and all. Thank you very much. And I'm winding up the today's class. It's now time 1:34. Okay, so any doubts? You also start preparation along with me. Like of course, I have been prepared this PPT for you people for better knowledge I wanted to provide. That's why I'm preparing this. I hope I'm up to your expectations. So with this, I'm winding up from my side. Thank you, one and all.
Thank you, sir.
Yeah, shall I leave?
Okay, sir.